Today we will be discussing previous year's question from CBSE or AirPass, and we'll be covering topics which is related to electrostatic potential and all the related concepts. Like we'll be discussing questions from electric potential energy. We'll be discussing questions from system of charges. We'll be discussing questions from potential and potential energy of a dipole. Right. So all the concepts which are related to electrostatic potential, so we'll be covering all the questions from such topics. Okay. So this is our first question. Now it is said that you're having a charge Q. A charge Q is uniformly distributed over a metallic sphere. Okay, so let's just consider a metallic sphere. This is my metallic sphere, and who is given a certain charge. So let's just say that you have given a Q charge to this sphere, and you have to find out the expression of electric field E and electric potential V at point 0 less than x less than r. That r is the radius, so let's just give him a certain radius. This is the radius value. The radius r. Our point is considered somewhere inside this sphere, as it is. You can see the condition 0 less than x less than r. So that 0 is nothing but my origin. So let's say that this is my origin O, or my center O. Okay, you have to find out electric field at point, let's say here. This is my point P, and this P point is at distance x from the center. So let's say that this is my distance x. Okay, so we have to find out electric field and electric potential at this point P. Okay. So first we will be finding out our electric field value, and then we will be finding our electric potential value. Electric field at point P at distance x from center O. We'll be finding out our electric field value. So to find out electric field, we'll make use of Gauss theorem. Okay. So applying Gauss theorem. Gauss theorem states that the number of field lines, or you can say the flux value, electric flux through any Gaussian surface, is 1 by epsilon naught times the charge enclosed by the Gaussian surface. This is what Gauss theorem says. So let's just understand here physically how we can apply this. So since we have to find out electric field at point P, so what we will do, we will first draw our Gaussian surface. Okay, which is passing through this point P. Okay, so this is my Gaussian surface, who is having that same center O, but this Gaussian surface is drawn with radius x. Okay, so we'll be finding out the flux through this Gaussian surface with radius x. Okay, so this is our flux value, and there is nothing but integration E dot ds. This is our net flux through this Gaussian surface, and it has to be 1 by epsilon naught times the charge, total charge enclosed. Total charge enclosed. But if you see in our diagram, okay, this Gaussian surface does not enclose any charges. All our charge is distributed uniformly over this metallic sphere. Okay. Since this Gaussian surface, who is having this radius x, since he is not enclosing any charge, so our this total charge value, this is going to be 0. Okay, since our total charge value is 0, so our flux value is going to be 0. So if I apply flux relation, nothing but integration E dot ds is equals to 0, so we can find out that inside the metallic sphere we don't have any uh, electric field. Therefore, inside metallic sphere there is no electric field. Okay. So this is our first part, how to find out the electric field value. Okay. Now, if I want to know what is my electric potential, so this is our first part. So what is our electric potential at the surface? Our electric potential at the surface of this sphere. So it is nothing but V equals to K Q by capital R. This is our electric potential at this surface. Now, since there is no, since you don't have any electric field, okay, so there will be no work done in moving a charge inside this shell. Okay, and since there is no work done, so therefore the potential inside this cell also, inside this sphere also, this value will remain same. Okay, since no work is done in moving a charge inside the shell. So since there is no work done, so obviously you will not have any potential difference inside the shell. So that means when you don't have any potential difference, so the potential inside the shell will remain constant at every point. So therefore, potential inside the shell remains constant, which is nothing but again K Q by capital R. So this much amount of potential we will see inside the shell. Always remember one point, that when a charge is moved from one point to another, we will have work done if there is any potential difference between those 2 points. So since you don't have any electric field inside the shell, and since you don't have any work done value in moving a charge from one point to another, so therefore the potential remains same. You don't have any potential difference. And what should be the value of that constant potential? The potential which you had at the surface, that same amount of potential you will see inside the shell. Okay, so this is our first part. Now we have derived the electric field value, and we have also derived the electric potential value at 0 less than x less than r. Okay, now we have to see that how we will be the variation, how the electric field varies with x. For this case, it is again 0 less than x less than twice r. We'll be finding out that part. Now, if I consider our x-axis and your y-axis, let's say that you are having an x-axis, and so let's just say that Along this axis, you consider your distance, and along this axis, you consider your, let's just say, electric field. Electric field. Since we don't have any electric field inside the shell, but at the surface, if it is asked, let's just say that a point somewhere here. If we are asked that what will be the value of electric field at the surface. So at the surface, let's just say that E suffix x. So we will have this much amount of electric field, k q by capital R square. This much amount of electric field we will have at the surface. Okay, at the surface. And if I consider your point somewhere outside the shell, then what will happen? This electric field is inversely proportional to R square. So he is going to decrease. Okay. So outside the shell, if I give this representation E suffix O, you will have this much amount of electric field AQ by small r square. Now this R will be a point somewhere outside the shell. Let's just say that this is that point, which is again considered from the center O. So as you move away from the shell, metallic sphere, okay, the electric field value decreases, right? So if I draw a curve, let's just say that this is my point O. You don't have any electric field from this center O to this point R, okay. But at the surface you are having an electric field now. Okay. Let's just say that this point is my radius R. So at this point you will have a constant electric field. Okay. Let's just say that electric field is E surface, which is nothing but k u by r square. This much amount of electric field at the surface. Beyond which if you go, then that electric field is going to decrease in this manner. And in our question, it is given that that distance x will be for distance twice r. So you can consider your point twice r. Okay. So this is the graph for electric field and distance x. Okay. For any point which is between 0 and twice r. Okay. So electric field will rise from this point r, that means from the radius or surface of the sphere, and then gradually it is going to decrease in this direction. So this is our first graph. Our second graph is asked for electric potential. So again we will be giving x-axis and y-axis as my distance, and your y-axis has to be your electric potential. So we will be providing this x-axis as my distance, and along this we'll be having now electric potential. Okay. And we have seen that inside the shell, inside the metallic sphere, we are having constant potential. Okay. So, and that potential is nothing but kq by r. But beyond, after outside the metallic sphere, your potential value again decreases. As you can see here, that this potential is inversely proportional to r. So the more further away you move away from your metallic sphere, the potential value gradually decreases. Okay. So you will have constant potential till distance r. Let's just say that this is that particular point, or you can say the radius of this sphere. This is my point O. So in this region you will have constant value, and that is again nothing but k u by r. This much amount of potential you will have. But after, or once you move away from the metallic sphere, then what will happen? It is going to decrease gradually. And since in our question it is given that you have to move up to this point twice r, so So you move up to point twice r. That's it. And this is my distance twice r. So this is the variation of electric potential with distance, from 0 to twice r. Okay. So this is our second question. Here it is asked that a charge Q is moved from a point A above the dipole, or dipole moment P, okay, dipole moment P, to a point B below the dipole in an equatorial plane without acceleration. You have to find out, what is our work done value. Okay, you have to find out work done value. Always remember, work done is nothing but work done in moving a charge. In moving a charge from one point to another, it's nothing but charge who moves from one point to another. In this, every time we consider that it is my test charge with the potential difference in between V1 minus V2. Okay, so this is how you find out your work done value. Now coming back to this question, so it is said that you are having a dipole. Okay, just give this is my minus Q and this is my plus Q. Okay, this is my dipole who is having center O, and the charge is moved along equatorial plane. Now, equatorial plane is something which actually passes through the center. Okay, this will be my equatorial plane. Okay, equatorial plane. This is my equatorial plane, and always remember, we have a different name for this equipotential. We also sometimes call it equipotential surface. Equipotential surface. Why we call it equipotential surface? Because at every point, your potential value is 0. Okay, net potential due to this minus Q and plus Q, at every point it is 0. That's why it is also called an equipotential surface. Okay. So if you move any charge, you are having a point A. For the question, point A is somewhere above the dipole. So this is my point, and he is moved to point B, somewhere below the dipole. I just say point B. Okay, you have to find out your work done value. So we have already stated clearly that in equatorial plane, the equipotential surface has the potential value is 0 here. Okay, so if any charge is moving over this equatorial plane, you will have no work done value. No work done. No work is done by charge Q in moving from A to B over equatorial plane. Okay, you don't have any potential at every point. You will have seen the potential. At this point also you will be having this potential value 0, and at this point also you will be having potential value 0. So you don't have any potential over this plane. So if the charges move from point A to point B, there will be no work done. Okay, so therefore no work is done. So this is our third question. Here it is said that you are having 4 charges, plus Q, minus Q, plus Q, minus Q, are arranged respectively at the four corners of the square of side ABC D of side A. How much work is required to put together this arrangement? So you need to find out the work done value. So we will just find out our net potential energy for this system. That net potential energy will give us how much amount of work it has been done by all these 4 charges to come into such arrangement. Okay, so let's just say that he's given certain names A, B, E, and D. A is having plus Q charge, B is having minus Q, E plus Q, and D minus Q. To find out work done, okay. So work required to put together this arrangement. If you remember, we had found out the expression of potential energy for different charge system. We had done that for two charge system. We have done it for three charge system. Okay. So when you find out potential energy, so we just see that how many pairs of charges are there in your particular system, right? So if you're having a two charge system, then you will have only one pair, and when you find out potential energy for such system, you will have only one expression. That means K Q1 Q2 by R12 for a two charge system, right? Okay. For a two charge system, okay, your expression for potential energy was something like this: K Q1 Q2 by R12. For a three charge system, when you find your net work done by all the charges, so it was something like this. Since you are having three charge system, so you have three pairs. Okay, so your net potential energy was something like this: K Q1 Q2 by R12 plus K Q2 Q3 by R23 and K Q1 Q3 by R13. This was the expression for the net potential energy for three charge system. Now this is a four charge system, so you will have four pairs: AB, BC, ED, EB, and BD, and AC. You will have six charge system, six pairs, and you will have six terms, individual terms. So when you add all those six individual terms, you will find out the potential energy for such system, and that will give you the work required to put together such arrangement. Okay, so we will find a potential energy for, let's just say, for the pair AB, then for the pair, let's say, BC, then CD, then AD, and then BD and AC. You will have six pairs and six individual potential energy expressions. Okay. So when you add all this six potential energy, so that will give you the work done expression for this entire charge system. Okay. So for AB, it will be minus Q plus Q by A. Okay, AB. So as it is mentioned in our question, so he is having site A. So let's just say that this side is having a length A. So that's why AB minus Q plus Q divided by A. This is between A and B. Again for BC also you will have seen K plus Q plus Q minus Q by A. Again for CD plus Q minus Q by A. Again for ED plus Q minus Q by A. And the rest two charges will be BD, U potential energy for the pair BD. So it will be K minus Q by K root 2. Okay, the diagonal length BD. And for AC also you will have same value, K plus Q by K root 2. Okay. So if you take into consideration all these four terms, so you will have something like this: minus K Q square by A. Since we have four terms, multiplied by 4 plus, say, this two term, so twice K Q square by A root 2. So if you take k q square by a common, you will find something like this: 2 by root 2 minus 4. And if you do further calculation, so you will have root 2 minus 4. Okay, so you can calculate, beyond that also, you take the value of root 2 and then you can find out your net potential energy. So you will have the potential energy expression as k q square by a root 2 minus 4. This much amount of potential energy, or you can say this much amount of work is required to put together this arrangement. Okay, so this is the first part of the question. Now in the second part, what it is asked, that a charge q naught is brought to the center of the square, the 4 charges being held fixed. How much extra work is required to do this? That means here what you will do, this is the second diagonal, and they intersect at this particular point. This is the second diagonal and they intersect at this point. Let's just say that this is point O, and at this point O, you want to place your charge Q naught. Okay, so what and how much extra work is required to put the charge Q naught at this point O? So that work done value you need to find. So for that, what we will do, we will find out the potential at point O. Since it is already mentioned in our question that all the charges, that means the plus Q minus Q plus Q minus Q at A, B, C, D, all those charges are held fixed, and we will be finding out potential due to all those charges A, B, C, D. So when you find potential at O, so that will be nothing but potential due to A plus potential due to B plus potential due to C plus potential due to D. And if you calculate all the other values, so you will have your net potential 0 at point O due to all the charges A, B, C, D. Okay, remember that OA equals to OB equals to OC equals to OD. Right? So all the potential gets cancelled when you're having plus sign and negative sign there. So when you find out your extra work, okay, work needed to bring charge Q naught to center, that is at O. When you do that, so our work done expression is nothing but Q naught multiplied by potential at that point, potential at point O, right? But in our question, but we have seen that the potential at point O is nothing but 0. So our net work done extra work is also how much? 0. Okay. So this is how we calculate the work done part when this charge is brought to a certain point. Okay. Okay. This is our next question. Now here it is asked that we are having 3 charges, plus Q, 2 plus 2Q, and minus 3Q. Placed are the 3 vertices of an equilateral triangle of side L. Okay, so this is my equilateral triangle. And A, B, C of side L, and you have placed, let's say, plus Q, plus 2Q, and minus 3Q. You place 3 charges. And the side of this triangle, let's say it is L. Let's say it is L. Now, if these charges are displaced to the midpoints A1, B1, C1 respectively, how much amount of work is done in shifting the charges to the new location? Okay, when you change the positions of these charges, say that you have brought A to a point A1. Remember, A1 is the midpoint of this side AB. You have taken the charge 2Q and you have brought it to another point B1. B1 is again the midpoint of BC, and you have taken the charge C and you have brought it to point C1. Okay, because C1 is the midpoint of AC. Okay. That means what you have done, you have changed the position of these three charges. So, and how much amount of work is done in shifting these charges? Okay, that you have performed. So it is quite simple. What you do is that you just find out the potential energy when the charges was placed at these 3 points A, B, C, and you find out the potential energy when you bring it to these points A1, B1, C1, and then when you difference and when you subtract those two potential energy values, that will give the extra work done in shifting the charges to the new location. Okay, so for a 3-charge system, you can see this is a 3-charge system. So for 3-charge system, we know our potential energy expression, which is nothing but U12, U23 plus U13. See these indexes, you can give it to any term A, B, C. I've given 1, 2, 3. You can give A, B, B, C, and C. In that way also it can be continued. So you have 3 pairs A, B, B, C, and C, A. So in that way you just put your potential energy expression. So K plus Q, 2Q by L. Okay. L is the side of this triangle. Again K plus Q plus 2Q. Okay, if I find it for BC, plus 2Q and minus 3Q divided by L plus K plus Q minus 3Q if I find it for AC divided by L. So this is the way our initial potential energy is. That's why I give the index I. So you have like how much? K 2K Q square by L plus, here you will have a negative sign, minus 6K Q square by L, and you will have minus sign, 3K Q square by L. So this will be our net potential energy in the initial condition. Okay. So if you do the calculation, you will get around minus 7 K Q square by L. So this will be our initial potential energy when the charges were placed at the point ABC. Okay. When the charges were at A, B, C. Right. Now we will do for the second case. The second case is what? You have brought those charges plus Q, 2Q and minus 3Q to the points A1, B1, C1. And since A1, B1, C1 are the midpoints, okay. So this is the line which is running ANC. This is for ANC. Sorry. For VC, and another will be for A1, B1. Right? As you can see here, A1, C1, A1, C1, and A1, B, B1, and C1, B1, C. So all these triangles, again, in addition to this A1, B1, C1, all these 4 triangles, they are all equilateral triangles. So this side, if you see here, this will be only L by 2. So he will also be L by 2, since it is the midpoint. Now since A1, B1 and B, this is an equilateral triangle. So this particular distance is also going to be L by 2. Right? So that means what we see here is that A1 B1, B1 C1, and A1 C1, all of them will have this L by 2 value. Okay. So when you find out for the second case, okay, that means when the charges are placed at A1, B1, C1, okay, so that will be our U final. So in that case, what you will write K plus Q, 2Q, but instead of L, you will have L by 2. Okay, then again K plus Q minus 3Q divided by L by 2. Then again you will have K 2Q minus 3Q divided by L by 2. This will be our final potential energy when the charges are placed at points A1, B1 and C1. The separation between them is how much? L by 2. Okay, and when you do the calculations, you will get how much? 4K Q square by L. You take 2 in the numerator. Here also you will get how much? 6K Q square by L. So you will have a minus sign there. And here you will have 12K Q square by L. So if you do the calculation, you will get how much? Minus 2 from here, and then again minus 2. So you will have how much? Minus 14K Q square by L. So this will be our net potential energy in the final position. Okay. Now when you find out the difference between these two, okay, work done. So that difference is going to give you the work done in shifting the charges, new location. Alright, because this potential energy, what we are actually finding, initial potential energy and the final potential energy, whatever expressions we are having, these are nothing but potential, and these are nothing but work done, right? So this initial potential energy, how we had expressed, we had calculated our work done. If we go back to our theory, which we had discussed in the last class, so this is nothing but an work done. Okay, and this expression is also nothing but work done. So when you are finding out the difference between these two, what you are doing, you are actually finding out the extra work. So that is why what you do is that you subtract this final potential energy and your initial potential energy, right? And when you do that, you get around something minus 7K Q square by L, right? So this much amount of work is required, to bring the charges. That means this plus Q, 2Q minus 3Q from the points A, B, and C to the points A1, B1, and C1. Okay. So this question number 4 is 50% is quite similar to question number 3. In question number 3, there also we had done something similar like this. We are having certain system of charge, and we were asked to find out the work required to bring this arrangement. So whenever you are asked such something like this, that you always find out your potential energy for that system of charges. Okay, so that's the potential energy is actually going to give you the work done. Okay, so this is our next question. So here you have to justify a statement. The statement says that for any charge configuration, the equipotential surface through any point is normal to the electric field. Okay. So first of all, let's just recall what is our equipotential surface. Okay. So we have understood that equipotential surface is that surface where potential at every point, potential value, let's say that potential at A, potential at B, potential at C. So at every point, potential value remains same, right? The potential values are equal to each other. You don't have any potential difference between between these points over that surface. And you have to show that this electric equipotential surface, it is normal to your electric field. That's what you need to show that. Okay. Now we have this relation. We know that we have a relation between equipotential, electric potential and electric field. It is nothing but E equals to minus dV by dr. This is the relation between electric field intensity and electric potential. So if we express our electric potential in terms of electric field, so we get something like this, right? But we know that for equipotential surface, there is no potential difference. That is, dV equals to 0, right? Because your V is constant there. Okay. So since your V is constant, so your potential dV part becomes 0. So you get something like this: E dot dr is equal to 0. Okay. Now since both of them are vectors, so if you take dot product of these two, so it turns out to be something like this. So that means the electric field E and dr, since dot product of two vectors is 0 here, and we see the dot products of two vectors will be 0 for only one condition, and when that condition is nothing but both the vectors are perpendicular to each other, right? So this electric field intensity E and this displacement dr, they are normal, means perpendicular to each other. Okay. So thus we can say that for any charge configuration, your electric equipotential surface through a point is normal to the electric field. Okay. Let's just say if I want to visualize this, let's say that this is my point Q, and if I draw two equipotential surface due to this charge Q. Okay. Now this first surface will be, let's say he is at distance R1. Let's say it is R1, and then again let's just consider another equipotential surface, and that will be a different position. Okay, so let's say that distance is R2. Alright, now this distance between these two equipotential surface, let's say that it is dr. The distance between these two equipotential surface, let's say it is dr. Right. Now, since this is charge Q and he is my source charge, so he is generating certain electric field. So he will be generating a radially outward electric field. Right. So since he is generating a radially outward electric field, so as you can see here, at every point your electric field or electric field line, they are normal to every equipotential surface. If I consider my first equipotential surface, so this field line is normal to this first equipotential surface. And again, if I consider my second equipotential surface here, so you can see that the field line is again normal to the second equipotential surface. Similarly, this displacement is normal to that particular equipotential surface. Okay. So this is how you are going to justify this particular statement. Okay. This is again a 2 marks question. So if you provide this mathematical explanation, and at the last if you make this point that that's why the potential surface through any point is normal to the field, so it is quite justified. Okay. Okay, so this is our next question. Now here it is said that you are having a dipole of length 4 centimeter, and this dipole is placed with its axis making an angle 60 degree with the uniform electric field. Okay, so let's say that you are having certain electric field. You are having certain electric field in this direction. Since it is uniform, so all the field lines will be parallel to each other. This is how you define a uniform electric field. And here you place dipole in such a way that the axis is making 60-degree angle. Okay. Let's say that this is minus q, and let's say that this is plus q. This is my dipole, and he is making an angle 60 degrees with this uniform electric field E. Okay, so our charge value is given to us. It is nothing but plus minus 8 nanocoulomb. Okay, plus minus 8 into 10 to the power minus 9 coulomb, and it experiences a torque. Nothing but 4√3 Newton meter. Right? So I've studied in the earlier classes that when you have a dipole and if you place it in any uniform electric field, so for both the charges you will have an oppositely directed Coulomb force. He is going to experience a force in this direction, and this minus q is going to experience a force in this direction due to this electric field E, and both the force cancels out each other. And since these forces are directing in opposite direction, so it provides a couple, and due to that oppositely directed force, the dipole experiences a torque, and due to that torque, the dipole starts to rotate about the axis, right? So here we have to find that how much potential energy this dipole is having. Okay, so that potential energy for this system we have to find it out. Right. Now, if you remember, we had expressed our potential energy for dipole as something like this, minus PE cos theta. Right. This is the potential energy expression for a dipole when it is placed in any uniform electric field E. Right. So step by step, we are going to do. Right. First, we are going to use our third expression, which is nothing but PE sin theta. Remember, the theta is the angle between the axis and the electric field E. Now in this case it is 60 degree. Alright. So if I put sine 60 there, 4√3. So sine 60 we get how much? 4√3 by 2. So 4√3. So this √3 gets cancelled. So PE value gets around E. We have this value E. Now, this potential energy U, if we replace this PE here, so our PE value is how much? 8, and cos theta, so cos 60 degree. Okay, so minus 8 multiplied by cos 60 is around 1 by 2. So you get something potential energy minus 4 joules. Okay, so this is the amount of potential energy this dipole is possessing when you place it in this uniform electric field E. Okay, and this question is very important because CBSE has asked such types of question number of times. Okay, so if a torque will be given to you, and you will be asked to find out potential energy. So from the torque part, you can easily find out your PE value, and you can replace this PE value in our potential energy expression, and that will give you your net potential energy. Okay. Okay. So here it is said that this was the last seventh question. So here it is said that 3 concentric metallic shells, A, B, C. Okay, we are having 3 concentric shells. That's why this is A, this is B, and the last one is C, with radius ABC. Okay, so is my radius A, this is my radius B, and the last one is my radius C. Given to these three metallic shells, A, B, and C, and all these three shells are having different charge density. Shell A is having plus sigma charge density, shell B is having minus sigma charge density, and shell C is having plus sigma charge density. We have to find out that what is the relation between this radii ABC when shells A and C are having same potential. Okay. Let's just recall what the potential concept which is related to a metallic shell. Okay. For any metallic shell, the potential at the surface is always KQ by R. The R is the radius for that shell, and Q is the charge distributed over that metallic shell. Okay, this is the amount of potential which we have over the surface. Even the same potential we have inside the shell also, because we have understood that inside an metallic shell there is no electric field. Electric field value is 0. It makes our potential inside the shell constant, and that constant value is nothing but this expression KQ by capital R. When we move away from the shell, okay, that means when you consider any point outside the shell, so your potential at that particular point outside is nothing but KQ by small r, where R is something very much greater than capital R. In this way, we had studied our electric potential for any metallic shell. Now, step by step, we are going to find out that how much potential and electric potential we have at the surface A and at surface C. We will be finding our potential at surface A and we will be finding our potential at surface C. And then we are going to make this potential equal to each other as per our question given. And then from that equation, we will be finding out the relation between this A, B, and C. Okay. Now, if I express my potential, electric potential due to a surface, so it is nothing but KQ by capital R. Okay. R is the radius of that sphere. But in this question, it is expressed in terms of charge densities. So we will express Q in terms of charge density. Now, charge density will be multiplied with your surface area. Okay, 4 pi r square, surface area for any sphere. When you multiply these two quantities, so that multiplied quantity gives us the charge which is uniformly distributed over the sphere, right? R. And when you replace this K value, it's nothing but 1 by 4 pi epsilon naught. So when you do the calculation, 4 pi r square by r, so you get something sigma r by epsilon naught. This is my electric potential in terms of charge density, surface charge density. So when we find potential at point, that means for the surface or metallic shell A. Okay, when we find potential at the surface A, so that potential will be addition of all the potential due to all these three charge densities, plus sigma, minus sigma, plus sigma. Okay, that means we will have potential with radii A, then we will have potential with radii B, then we will have potential due to radii C, and all this small a, small b, small c radius are having this much amount of charge density, plus sigma, minus sigma, and plus sigma. Okay. We will make use of this expression, that means sigma capital R by epsilon naught. Right. So for surface A, we are having plus sigma charge, and the radii is A by epsilon naught. Sphere with radii B is having minus sigma charge density, so you get a negative sign, multiplied by radii divided by epsilon naught. and our third shell with radius or radii c having charge density of plus sigma multiplied by c by epsilon naught. Okay, so this is how potential at the metallic shell A is calculated. So if you take sigma by epsilon naught common, so you get something A minus B plus C. So this is the net potential at the surface A. Okay. Now we'll be finding our potential at surface C. And remember, when we find potential at surface C, so the process is little different. Okay. So if we take into consideration this equation, like we will be having three different terms, that's for sure. That means potential due to A and then potential due to B and potential due to C surface itself. So when we find potential due to C, so it will be nothing but sigma C by epsilon naught. Okay. But when we find potential due to A, now remember this surface A is inside the shell C. So for that, what will happen? It will be sigma. Now since sigma charge density is distributed over this sphere A, so he will have a surface area 4 pi r square. Remember, when we find our charge value, we multiply the charge density with the surface area of that particular sphere. So when we find potential due to sphere A, and who is having plus sigma charge density, we will multiply this sigma charge density with the surface area of this sphere A. So it will be 4 pi A square divided by 4 pi epsilon naught C. Now this C, why we have written? Because we are finding out potential at the surface C. And remember, this R is nothing but the distance at which you are finding your potential. But in this case, we have considered that we are finding out at the surface, so that is why this R becomes equal to the radius of that sphere. Okay, since we are finding out for the sphere C, so this R has been replaced by the radius of this sphere C. So that is why we are having this C term. Okay. Similar process we will do it for this shell B. Okay, now this shell B is having minus sigma charge. So when we find out our charge value, we multiply with the surface area of the shell B, which is nothing but 4 pi B square divided by 4 pi epsilon naught, right? And then again we will write C here because again we are finding a potential at shell C. So that is why this distance C is coming. Okay, plus sigma C. Now here you will not see any change because you are finding potential at the surface of shell C, and then again you are considering the charge density of this same shell only, which is nothing but plus sigma. So you multiply this plus sigma with the surface area of this shell C, and that's why you get this expression only. That means sigma C by epsilon. Right? Remember, we are making use of this equation, but here since the surface area value is different, so that is why we are using different surface area values. Okay, for the shell A we are having 4 pi A square, for the shell B we are having 4 pi B square. This thing is different, otherwise the process is the same, like whatever we did it here, the same process we have applied. Okay, so if we cancel out this 4 pi there, 4 pi 4 pi. Okay, so you will have bracket sigma 4 pi. If you cancel 4 pi, so you get something sigma A square by absolute naught C, and here you get sigma B square by absolute naught C, and here you get sigma C by absolute naught. Okay, so these are our two potential values, VA, and this is my VC. Now we will make this two potential equal to each other. Okay, and when we make these two potential equal to each other, then only we will be able to find out what is the relation between this radii A, B, and C. Okay, so when we make VA is equals to VC, so you get we will replace this VA term with nothing but sigma by absolute naught A minus B plus C. You replace VC term, which is again sigma by absolute naught. If you take common there, you get something A squared by C minus B squared by C plus C. Right. So if you cancel out this two, sigma by absolute naught and sigma by absolute naught, so you get something like this, A minus B plus C. And here you get these A square minus B square plus C square. You take C LCM there. And when you do further calculation, so you get AC minus BC plus C square, and here A square minus B square plus C square. C square gets cancelled. Let me just rub this part. So you have, if you take C common, and you have like A minus B, you have like A square minus B square. So if you bring it to this identity, A plus B, A minus B, and if you cancel out this A minus B, so you get this relation, C equals to A plus B. Okay. So this is the relation between this radii A, B, and C. When you use this condition, that is, VA is equals to VC. Okay. See here from this part it is not that quite tough. You are going to express this. But here our important point is that how you find out your VC value and how you find out your VA value. This was very important. I hope you have understood this part. Okay. So always remember that when you find out potential and when you bring it in terms of charge density, always remember we use this expression only, K Q by R. It's just that you have to check that this Q, when you multiply charge density with the surface area, you have to check that for which surface you have considered, whether you have considered for the same surface. If you consider for the same surface, then there is no such issue because that same R is going to come across. Okay, but if you consider surface charge density for different surface, then you will have different term. Let's say E square or whatever. You will have different variables here if you consider for different spheres with different charge density. Okay. Only this modification you have to apply. Otherwise, the process is same. Okay. Okay. So in this question, you can see that the point charge Q is placed at point O. Okay, shown in the figure, and you have to find out what is potential difference VA minus VB, whether it is positive, negative, or zero, provided that your charge is positive or if your charge is negative. Based on this positive negative sign convention of charge, you have to find out the sign convention of the potential difference. Right. So let's just say that you are having certain charge at this point. So this is point O, and you are having charge Q. And you are having two different points. Let's say that this is point A and this is point B. And this distance, let's say it is R suffix A, and this distance, let's say it is R suffix B. Okay. So let's say the potential at point A is B suffix A, and potential at point B, let's say it is V suffix B, right? Now, from earlier topics, we have understood that potential due to a point charge, any point charge, so it is nothing but 1 by 4 pi epsilon naught Q by R. Okay. R is the distance from the point to the charge. Now here, as per this diagram, we can clearly see that RA is greater than RB. Sorry, RA is less than RB, and greater. I'm sorry. So RA is less than RB. Okay. So first of all, if I consider that my charge, to be positive, okay. So here, our first assumption is our charge is positive. So in that case, what will happen? Potential at point A will be greater than potential at point B, because electric potential and resistance is inversely related. So that is why you will have opposite sign convention. So therefore, we can say that VA minus VB, you will have positive value for positive charge convention, sign convention. Okay. Now, second point, it is given that if your charge is negative, so when your charge is negative, this sign convention gets reversed. So that means potential at A becomes less than potential at B, because of the changing sign convention of the charge. You are having reversed potential difference sign convention. So therefore, you will have VA minus VB as a negative value. Okay. So in this way, you have to solve such questions. You have to see the sign convention of the charge. Based on the sign convention, you have to determine whether your potential at a particular point, so it is greater than the other potential or not. And based on that only, you will be able to find out the potential difference. Okay. Okay. So here you can see that a figure is given, and it is said that two graphs shows the variation of electrostatic potential with 1 by R. R being the distance of the field point from the point charges for 2 point charges Q1 and Q2. Okay. So this curve is for charge Q1 and this curve is for charge Q2. Along this direction you are having 1 by R, and along this direction you are having potential, electric potential. Okay. So you have to find that what are the sign conventions or what are the signs of the two charges. And secondly, what you have to find is that which of the two charge has a larger magnitude and why. Okay. So if we see our electric potential expression, it is again KQ by R. Okay. Now, even though V and R, both of them are inversely related, but if I see the relation between V and 1 by R, then both of them are directly related. Okay. So they are directly related. So that is why you are given a variation between V and 1 by R. Okay. So see, you have to understand the difference between what should be the relation between V and R, and the relation between V and 1 by R. When we say relation between V and R, it is inversely related. And when we say the relation between V and 1 by R, it is directly related. Okay. So here in our question it is mentioned, you have to find out the relation. Here the relation between V and 1 by R is provided to us. And based on this relation, you have to see the sign convention of the charges Q1 and Q2. Now, this diagram, it shows very clearly that since Q1, this curve, this plot is in the first quadrant, So Q1, he will be positive, and since Q2 is in my fourth quadrant, so Q2 will be negative. Okay. So these are the sign convention of the charges. Sign of two charges. Secondly, it is asked that what should be the magnitude of the charges. Now, which charge will have greater value? That you have to find. It is very easy. You have to remember this point, that slope of V and 1 by R graph. Slope of V and 1 by R graph is proportional to the value of charge. Okay, that means slope of V and 1 by R graph will provide us the charge value, the magnitude of the charge value. Okay. Now, if you remember what is slope, the slope is nothing but tan theta, is again nothing but perpendicular by base. So when you find out the relation between the ratio between potential and 1 by R value, so that will give you potential and 1 by R value. So that will provide you the magnitude of the charge, how much it is given for the graph. Now, as you can see here in this, the slope, or you can say the angle made by the Q1 plot and the angle made by the Q2 plot. Now, there is a large variation in between. The Q1 plot or Q1 curve is actually making lesser angle as compared to Q2 plot or Q2 curve. Okay, so since angle, or you can say, that instead of writing angle, you can directly mention slope. Slope of Q2 is greater than slope of Q1. So therefore, magnitude of Q2 is greater than magnitude of Q1. Okay. So if I want to represent my slope, so it will be something like this. Let's just say that you have considered two different points, and if you try to draw a triangle there, let's just say that this is my one side, and this is my other side. Okay. So this particular part will give us V value, the potential part, and this particular part will give us 1 by R value. Okay. Now, how we had said that the slope is proportional to the charge Q. So if you go back to this relation, V equals to K Q by R, and if you try to find out the ratio between V and 1 by R, so you will find that the ratio is something KQ. That means this V by 1 by R, this is proportional to charge value, and this V by 1 by R, this is nothing but slope of V versus 1 by R. Okay, so all you need to know is that the slope value for such graphs, and that slope is going to give you the magnitude of the charge value. Okay. Okay. So this question is very important. You're given two different figures. One of the figure is for positive charge, two is having a radially outward electric field, and in the second diagram, as you can see, you're having a negative charge. So you're having a radially inward electric field. and correspondingly you are having two different points. In the first diagram you are having P, Q, and the other diagram you are having A and B. Okay, two different points are given. And both of them, all the points are at different distances from the respective charges. Now you have to find out various points. CBSE has asked a question of this pattern number of times, but I have accumulated all the questions and I'm providing it in a single question. I'm trying to provide it in a single question. Like you are having, they will be asking you, what are the sign conventions with respect to potential difference, then with respect to potential energy difference, then with respect to kinetic energy and potential energy. Okay. So I have accumulated all the questions, whatever CBSE has asked in previous years, and then provided you in this single question. So let's just try to answer all the questions one by one. So here, if you see first point, it is asked that give the sign of the potential difference Vp minus Vq and Vb minus Va. The similar question you have done one question earlier, that how you will be finding out the sign convention of the potential difference for different points. So if I consider my first diagram, let's say that this is my diagram A, and let's say that this is my diagram B. Okay. If I look into the first diagram, so here you are having a positive charge, and you are having two different points Rp and Rq. As you can see very clearly that Rp is lesser than Rq. Right? Point P is at much closer distance to positive charge as compared to point Q. So definitely your potential at P will be greater than potential at Q. So if I make use of this equation, which is nothing but 1 by 4 pi epsilon naught Q by R, right? So this potential is actually depending on this charge value, magnitude of charge, and the distance. So here, since the sign convention of the charge is positive, so we will be using the distance factor to answer the difference between potential of the points P and point Q. So since V suffix P is greater than V suffix Q, so definitely Vp minus Vq will be greater than 0. Okay, hence it is nothing but positive. Right? Now if you see this equation, even though Ra is less than Rb, but here our charge which is provided in this question, that is negative. Q is negative here. Okay, which is again K capital Q by R. Now since Q is negative, so here what will happen? V suffix B will be greater than V suffix A. Right? Since the sign convention of the charge provided here is given opposite sign, so that is why the potential values, at their different points, they also get reversed. So that is why the point which is at further away from our source charge, so that point will have greater potential as compared to the point which is closer to our source charge. In general, this potential and this distance is inversely related. So if you have lesser distance, it will provide greater potential. If you have more distance, it will have a lesser potential. But in this case, we cannot apply that because here our sign convention of the charge is opposite, which is negative. So that is why point B will be having greater potential as compared to point A. So in this case, when you find out the potential difference VB minus VA, so it is going to give you a certain positive value again. Okay. So in this way, you have to find out that for a given charge, source charge, and different points are mentioned to you, how you will find out whether the potential difference is negative or positive. So in this way, you have to do that. Okay. So this was our first question. Now, in the second question, it is asked that give the sign of the potential energy difference of a small negative charge between the points Q and P and A and B. Okay, so we will be finding out potential energy difference. Now, when we talk about potential energy, it is nothing but work done, right? That work done is actually going to provide us the potential energy value, right? So what we will do, we are going to provide, as per it is given that you are going to provide a negative charge. So let's just give negative charge to this point Q. So let's say that you are having a negative charge minus Q naught, right? So when you find out work done for this negative charge Q naught, okay, work done at point Q. So it will be nothing but minus Q naught multiplied by potential at Q. Right? So that will provide us the work done in bringing this negative charge Q naught from infinity to point Q. Right? So if you replace this potential value, which is again nothing but K capital Q, right? This is the positive charge. Okay. Divided by instead of writing capital Q, let's just write small q. Small q, positive small q. That is, this is my source charge, small q, divided by R capital Q. So as you can see here, it is nothing but a negative Q naught by R capital Q. Right? So this work done is something negative value. We are having a certain negative sign there. So it should be less than 0. Again, when you find work done at point P, let's say that now instead of putting that negative charge at point Q, let's say that you have kept it at point P. Okay, so this is now our test charge, and this test charge will be placed at point P, and it will be brought from infinity to point P. Now, how much amount of extra work you have done by this Q naught charge? So that we are going to find. So that will be nothing but minus Q naught multiplied by potential at point P. So when you find out potential at point P, it is again nothing but K Q by R suffix P. Okay. So when you find out this value, it is nothing but K Q naught by R suffix. So it is again negative. So this will be again less than 0. Right? But there is a slight difference. If you see this distance RQ and if you see this distance RP, right? So RP is much smaller than RQ. Alright. So that means work done which you have done for this Q naught charge at point P, so he will be more negative. Alright. Since this distance RP is much smaller as compared to RQ. Now due to the sign convention provided here, so this work done for P will be much more smaller as compared to work done for Q. So when you find out potential difference, let's say work done for Q minus work done for P, it is provided in our question. So that will be again greater than 0. Now both of them are negative, but if I compare work done for Q and if I compare work done for P, so he is little positive as compared to this. Okay, since he is much more smaller as compared to the work done for Q, so that is why the difference between them will have a certain positive sign. Okay, so this is how to find potential energy difference when you use a negative charge at different points, and when you find out potential energy value. Okay, similar process we are going to do for this negative charge. Now, Here also, what you are going to do is that you are going to place negative test charge at different points. So initially, what we will do, we are going to place Q naught charge at this point P. Okay, and we are going to find out that how much work has been done by this Q naught charge in bringing from infinity to point P. Okay, so when we find our work done for B, so it is nothing but again minus Q naught multiplied by potential at B. So if we express potential at B, so it is again nothing but K minus Q by R suffix B. So we will get a positive work done K Q naught by R suffix B. So this is the work done in bringing a test charge minus Q naught from infinity to point B. Similarly, again we are going to do the same thing. We are going to find out our work done at A, now which will be seen as B only, which is nothing but K Q Q naught by R suffix A. Now since R suffix A is less than R suffix B, okay, so therefore work done for B is greater than work done for A. And when you find out the potential difference between these two, so it will be again greater than 0. That is, it is again positive. Okay, so in this way we find out our potential energy difference for different points when you use a negative charge at different points. Okay, so this goes our second question. Okay, now if you see our third question, so it is asked that give the sign of the work done by a field in moving a small positive charge from Q to P. Okay, so that means you have to move a small positive charge. Okay, let's just say that that small positive charge is Q naught, and is being moved from point P to point Q. In such case, you find your work done value as nothing but multiplication of the test charge with the potential difference between Q and P. Now, since this charge Q naught it is being moved from Q to P, so that means the potential difference will be VQ minus VP. Now, in the earlier points, let's say in the point A, we have seen that what should be the sign convention of potential P and potential at Q. Okay, so we have seen there that potential at P was greater than potential at Q. So therefore, this difference VQ minus VP is something negative. Okay, since this potential difference is negative, so this work is also going to be negative. So here, work required to move Q naught from Q to P is negative. Okay, so this is how you find the sign convention in moving a test charge. Similarly, if you see point D, here also you have to find the sign convention of the work done by an external agency in moving a negative charge from B to A. Now in this case, for this diagram, you are having a negative charge, let's say minus Q naught, and this negative charge has been moved from B to A. Okay, so we are going to do the same way only. We are going to find out work done as nothing but negative charge of minus Q naught multiplied by the potential difference between B and A. Okay, now if you see minus Q naught, so it is nothing but VB minus VA. Right. Now, from this earlier point A, we have seen that potential at B is greater than potential at A, right? Because you are having a negative source charge now. Now, since you are having a negative source charge, so therefore this work done in moving this minus Q naught from B to A, right? So in this case, he is positive. The difference is positive. So therefore, your work done is also positive. That is, work done is greater than 0. Okay, so here the work in bringing this minus q naught charge from B to A, that is also positive, right? So this goes our point D, right? If you see point E, so this is quite similar to D, right? Okay, here in D, question number D, we have seen how much work is done, right? And what should be the sign convention of the work in bringing this minus q naught charge. So always remember, and whenever we define work, it is nothing. We are actually defining or discussing about potential energy. Okay. So when we say that the work done in bringing this minus q naught charge from point B to point A is positive, so that means our potential energy value in bringing from B to A is increasing, since you are having a positive sign convention. Okay, so that is why this potential energy increases in bringing from point B a negative q naught charge from point B to point A. Okay, but we have studied in class 11 that whenever you are having an increasing potential energy in any kind of motion, so there will be a decrease in kinetic energy, right? Since in this case we are having increase in potential energy, so here it is asked that whether the kinetic energy of that small negative charge will it increase or decrease in going from B to A. Now, since point D says that potential energy increases, so here we can make a point that since potential energy is increasing, so what will happen? The kinetic energy, whose kinetic energy? The kinetic energy of this negative charge, that is Q naught. So kinetic energy of minus Q naught decreases. Okay, decreases from B to A. Right. So in this way, the CBSE has been asking questions, in such patterns. So these points are very important. Whatever I have mentioned it here. Okay. I'm going to make a point that this question is very important from both point of view. Right. Okay then. Thank you.